All right, so we're going to look at some serial synthesis problems, and what I'd like to do is simply start with this particular problem where we have a terminal alkyne. So notice that it doesn't have two acidic hydrogens that can be removed, only one. And we are going to make a carbonyl that also has an alpha, beta, gamma hydroxy. So we're talking about a gamma hydroxy carbonyl. You can approach this problem one of two ways. Probably the smartest move is to do the retrosynthetic analysis that E.J. Corey formulated at MIT. So we have an anti-Markovnikov alcohol because it's a terminal primary alcohol. And so our first disconnection, we know that we need to do, in the very last step, a borohydration procedure where I use BH3 and THF. And of course, in the second step, in the oxidative step, we'll use hydrogen peroxide and NaOH or KOH. So this will convert a terminal alkene into this gamma hydroxy group. So we know that our immediate precursor needs to be precisely what we have in our product, with the exception that rather than having this primary alcohol, we have this unconjugated enone. I can do a better job of drawing that, so let me fix this real quick. So this is a logical last step. Now, before we had the carbon-carbon double bond, we've learned in class that we can reduce this from a carbon-carbon triple bond. So let's go ahead and do that. And I think just diatomic hydrogen with a palladium catalyst would work, or a platinum catalyst would work, or a nickel catalyst would work. Those are all in the same group in the periodic table. Just select one. And then, of course, the precursor is a different terminal alkyne. Of course, our carbonyl is still in place. It's real important when you do this not to drop carbons as well. And again, I'm going to fix my bonds. So we still have 1, 2, 3, 4 carbons. Now, this carbon-carbon triple bond that I have currently is not the same carbons as the initial carbon-carbon triple bond. So this probably came through an SN2 reaction. So all we need is ethyne, or the anion of ethyne, as our nucleophile. So why don't we just use this molecule as our nucleophile in the reaction. And then a bromine leaving group probably makes a lot of sense here. Now the question is, how do I get this functionality from an alkyne We actually saw this on the last exam. If we use Br2 and H2O on a terminal alkyne, once it's been appropriately deprotonated, so I'm going to just do a small aside here. When I will make a bromonium ion intermediate, of course, this is even more strained than usual because of the carbon-carbon double bond. And one of these carbons, of course, is bonded to the cyclopentyl functional group. The other one has a hydrogen. Water acts as a better nucleophile as opposed to Br-. And the carbon that's most electrophilic is actually the one I'm rendering in red because it's more substituted. And so water attacks SN2 and this bond breaks. What I get after another proton transfer is kind of sort of a halohydrin, but I still have a carbon-carbon double bond. And so I have a vinyl alcohol that can easily undergo tautomerization. And when it undergoes tautomerization, I will have a base, where I deprotonate, form a carbon-oxygen double bond, and then probably HB, which was produced in the first proton transfer, will donate its hydrogen to complete the carbonyl. And so this shows mechanistically quite nicely how we can obtain this functionality by taking a terminal alkyne and reacting it with Br2 and H2O. So terminal alkyne, Br2 and H2O to yield an alpha bromo ketone. And then that can undergo SN2 to give another terminal alkyne that I can hydrogenate. Notice cis and trans isn't relevant here. And so when cis and trans isn't relevant, you just get a terminal alkene, and then we can hydrate this double bond through borohydration. All right, here's one that's even more unique. And so when I look at the reactant, which has this terminal alkyne, and I look at the product, I certainly know that I'm going to need to do something to this triple bond. And one thing that I want you to notice in your analysis, you have a T-butyl group in your product. You have a T-butyl group in your reactant. And so these two carbons right here are analogous to these two carbons right here. So I'm going to emphasize those in black. This means probably one of the first things I'm going to do is to get rid of this triple bond and to somehow have a hydrogen and a chlorine attached, or even better yet, to have a chlorine and a chlorine attached. In order to do this, I need to reduce this triple bond to a double bond. So let's go ahead and, on this problem, I'm probably going to work, rather than working backwards, I'm going to work from the front. So let's go ahead and reduce this. And it doesn't matter if I use Lindlar's catalyst or if I use, sodium and liquid ammonia or lithium and liquid ammonia. Because sodium and liquid ammonia is the cheaper reagent, I'd probably go with that rather than Lindlar's catalyst. So let's just do that. Sodium and liquid ammonia to give this terminal double bond. Then I can subject this double bond with molecular chlorine. And I'm going to use molecular chlorine because I already have a chlorine already integrated into the atom. There's no sense in doing bromination and then replacing it. And of course, once I do this, I'm going to get an anti-addition of diatomic chlorine across this double bond. Now, the configuration at this carbon really doesn't matter because it's not chiral, but it really does matter here. And I want you to notice that the stereochemistry is not relevant because the maker of this molecule, or the maker of this test question, isn't making the stereochemistry relevant, which greatly simplifies your task. So at this point, we have the T-butyl group and this carbon. This is all taken care of. Now I need, of course I have a carbon here. I need 1, 2, 3 carbons. So one thing that we can do is to react this with a terminal alkyne again in an SN2 reaction. This isn't great reagent drawing, but it gets the job done. And what we'll have at this point, of course we already know that this part's already locked and loaded. So we already have this. Now we're making a new carbon-carbon bond. So let's just continue this. And if you carefully compare the backbone of this and this, everything is in place. So what we want to do now is reduce this triple bond to a double bond. And then we can do an acid catalyzed hydration of the bond to make an ether, which means we'll use an alcohol rather than using water. So to clean this up, in the first step, we can just do sodium and liquid ammonia again. In the second step, you could use a strong protic acid like H2SO4. And then rather than using water, simply use ethanol. Because you need to make the ether. Look at this functional group in the product. You have an ether. If this was an OH, you'd use water. And then you come to your target molecule. T-butyl group. Again, I'm showing a stereo-specific product, but it doesn't matter because you're not asked for it. And then we have 2 CH2s. and here's where our ether will be. And also, this squiggly line means we're not committing to a stereoisomer. You got 2 chiral centers in this molecule. You've got one here, and you've got one here. This problem would be much more advanced if you were asked to do this stereo selectively. But that's certainly how you make the bond. So we did one example where we work backwards, one where we work in the forward direction. Notice that we can do things to the triple bond besides just alkylating it. We can reduce it and then do electrophilic addition to the alkene product.